Hello friends, today's question. A pendulum is executing simple harmonic motion and its maximum kinetic energy is K1 if the length of the pendulum is doubled and it performs simple harmonic motion with the same amplitude as in the first case, its maximum kinetic energy is K2. So we have to find out the relationship between K1 and K2. So this is a very interesting problem because in the normal process we tend to use the basic formula, and let me write it here, and that is also going to give us answer, but that answer will be, or rather we can say that is the incorrect way of solving the question. So normally what we are going to do, we are going to write that kinetic energy is given as half m v square, and let us suppose the velocity is given a maximum through the, we can say, mean position, and Vmax will be given as W into A, where A is the amplitude, omega is the angular frequency, and omega will be given as G by L. So if we substitute these values, we are going to get kinetic energy will be equal to, this will be our half m, and this becomes GL, and this comes as A square. Now if you double, and this is initial, that is K1, and if you double the length, so if you simply double the length, we are going to get K2, which will equal to half m G upon 2L, and this will be our A square. So in this case now, if you find out the ratio of, you can say, K1 and K2, so we get K1 by K2, so obviously this cancel out and this becomes 1 by 2, and let me check, K1, K2 in the denominator, so this will be 2. So from here we can say that K2 will be coming as K1 by 2, okay, and it is one of the options available there. But the problem is that this is not the correct answer, and neither this is the correct way of solving the question. The issue lies that all this, the kinetic energy equation which we have used in this case, is based on the conservation of the energy principle, and in that conservation principle the length is taken as L, and in the entire process the length doesn't change. Whereas in this case it states that the length is doubled. Okay, no doubt we are doubling the length, but the basic formula which we are using in this case is derived on the base of the conservation of energy, and that conservation of energy results in us all this relationship. So this is, you can say, not the correct way to solve this particular question. Okay, you can say not correct approach. So now if you are going to use the conservation of energy, so we already know that for the conservation of energy, it states that we know that the potential energy is maximum at the extreme and kinetic energy is maximum at the mean position. Okay, so principle of you can say conservation can be used such that the potential energy at the extreme should be equal to the kinetic energy at the mean position. That's the basic premise of the conservation of energy. Okay, let me write it here. So you can say by conservation of energy, we know that at maximum displacement, which is nothing but our highest point, we have potential energy is maximum, and at the lowest point, which is our mean position, kinetic energy is maximum. Therefore, the conservation of energy potential energy at the highest point, is equal to kinetic energy at mean position. So this is the basic, we can say, conservation energy, and this energy is also law is also applicable at any point between the one extreme to other extreme. And so based on this, we can solve it by using conservation of energy. And second method is also there by finding out the amplitude that is based on your value of theta. And in this case, we are going to assume that theta is very small. So there are two methods, and with both methods, we are going to get the same answer. So let us first of all use first method, conservation of energy. So let us say when length is L, when length of pendulum is L. So in this case, we can draw the figure where length is L. So this is the mean position of the pendulum, and it goes from one extreme to the other extreme in this way, and this will be our minus A, and this will be a plus A, and this we have a mean position. And length in this case is L. So the height by which the bob or pendulum rises above the mean position, let us suppose in this case is given as h1, and this angle is theta. So this will be coming as L cos of theta. So we have, in the first case, when the length is L and minus, you can say, extreme position plus extreme position, and this is the mean position. So therefore, we can write this is h1. So you can see height through which pendulum rises is given as h1, and we can find out h1 will be equal to L minus L of cos theta. Taking L as common, this will be 1 minus cos of theta. And this extreme position, we can say that its potential energy will be because of this height. Therefore, we can say potential energy at h1 will be equal to mgh1. So this will be over mgl1 minus cos of theta. So this is our first case. The second case, when the length is doubled. When the length of the pendulum is doubled. So once again, let's draw the diagram. So this is the mean position, and this, in this case, states that it always goes from minus a to plus a. Okay, the same amplitude is there. So this is the position. So this will be angle theta once again. Now the length is 2l, and in this case we assume the height through which pendulum rises above the mean position is given as h2, and this will be our 2l cos of theta. So in this case we say that height through which pendulum rises is given as h2, and we can find out h2 will be equal to our 2l minus 2l cos of theta, taking 2 as common, 1 minus cos of theta. So potential energy at S2 will be equal to mgh2, and this will be equal to mg2l 1 minus cos of theta. So now we are going to use the conservation of energy, and the potential energy at the highest point will be equal to kinetic energy at the mean position. Okay, so we found out the potential energy at the highest point, and in first case we say, or rather it is given, that when the length is L, the kinetic energy is maximum. So the kinetic energy will be maximum at the mean position, and that will be equal to K1. So at mean position, you can say kinetic energy is maximum, which is given as K1, and in this case this is a mean position, and in this case also kinetic energy is maximum, given as K2. So using conservation of energy, potential energy at H1 will be equal to K1. So this gives us mgl 1 minus cos of theta, and potential energy at S2 will be equal to K2, and this gives us mg twice L 1 minus cos of theta. Now finding out ratio of K2 upon K1. K2 upon K1 will be equal to mg 2L 1 minus cos of theta, and this is mgl 1 minus cos of theta. So here mg, L and 1 minus cos theta goes, and this comes equal to 2. Therefore we can say that K2 will be equal to twice of K1. K2 is equal to twice of K1. So you can clearly understand that if we have used the principle of conservation, or rather we can say this formula, which were derived based on the length L, we have got the answer as K2 K1 upon 2, and which was obviously the wrong answer. Okay. The correct answer is K2 is equal to twice of K1. And in the second method, we can use, you can say, small angle theory. And in this case, we see this is the mean position and it moves through a distance of a. This is the theta and we have this as L in the first case. So we can say from here theta is equal to AL. So let us use that K1 will be equal to half m omega square, and we have a square, and omega is equal to g upon L square root, and a is equal to theta L. A is equal to theta L. Therefore, we can write that K1 will be equal to half m g upon L, and this comes as theta L square. So which, solving further, this will be giving us half m g L theta square. So first case. Similarly for the second case, this A is same, so this here will be A. Now this will be about 2L and this angle theta. In this case, the theta will be equal to, you can say, A will be equal to theta into 2L. Now we are going to get K2 will be equal to, and in this case omega will be equal to square root of 2L. So we are going to get K2 half m and g upon 2L, and this will be 2 theta L and whole square. This comes twice and become half m GL theta square, and this is nothing but our K1. So we get K2 is equal to twice of K1. So if we use small angle theory, we are going to get the same answer. Okay. So in this case, the only difference between this solution and the solution, in this case also we are going to use the original conservation of law, but the only difference will be the amplitude is, sorry, not amplitude, but the arc which is being moved by the pendulum is found out by as a dependent function on the length L. Herein there is no such thing, we did it. So that's why we are not getting the correct answer. So if we see the option A will be the correct answer. So option A is the, you can write option A is correct. This completes the question. Thank you.